In this exercise, we are asked to find an equation of the line that is tangent to the graph of f, where f is given to us here in algebraic form, and we want this line to also be parallel to the given line, given here, also in algebraic form. But before we get too wrapped up in the algebra, I found that over the years, a number of students just get kind of baffled right off the bat by conceptually, what is it we're being asked to do? So let's address this conceptually first. So we're given some function f, and again, we'll ultimately deal with it algebraically, but let me just draw a picture of some function, a graphical representation of f. And if you're inclined to be picky and say that's not a function, it doesn't pass the vertical line test, I'll do that just for you there. Okay, so now there's my function f graphically, and we're going to be given a line algebraically, but again, I'm going to draw it graphically here. And conceptually, what is it we're trying to do here? Well, we're supposed to find an equation of a line that is tangent to the function f, and we know there are infinitely many lines that are tangent to f. There's one right there. Here's another one right here. Here's another one right here. There are infinitely many tangent lines, but we only want the one or ones that are parallel to the given red line there. So I really only want that one. Or looks like there's another one too, right? That one. So the phrasing of the question suggests that there's only going to be one in the exercise that we're dealing with, but we should be open to the idea that sometimes there's more than one. And theoretically, there don't have to be any, right? So, but on this picture here, let's think of what it means for two lines to be parallel now. So when you're given the algebraic representation of this given line, I'm going to trust that using your old school math skills, you could pretty easily find the slope m for that given line. And recall that in this grown folk world of calculus, what is it that gives us the slope of tangent lines? Well, that's exactly the job for f prime. So if you're going to have these two lines be parallel to each other, doesn't it make sense that we're going to set those two equal to each other? So our game plan here is to find out what the slope of the given line is. That's going to be a constant, just a plain old number. And we're going to set it equal to the function f prime of x. And then ultimately we're going to solve for x, and you'll see where it goes from there. But at least we have kind of a game plan and a sense of what it is we're being asked to do and how we're going to go about doing it. All right, so let's bring the algebraic representations back up here. And another habit I would really like you to get into is to, before you jump into the algebra, again, think of what it is that these equations represent. What do they look like graphically? What does this function look like? What does the line look like? And while your inclination may be to reach for your graphing calculator, there are many times where you're not going to have that option. There are many times where the calculator is going to be barred from our activities. So let's think of how we can determine what this function looks like graphically. Well, again, this is some old pre-calc skills. Let's think of what's going to make a vertical asymptote there. Whenever you've got a rational expression, or more accurately, a fractional expression here, what is it that's going to, we see that the numerator is non-zero, but what's going to make the denominator equal to 0? That's the situation that tends to give us vertical asymptotes, right? So we see that an x value of 1 is what's going to give us a 0 in the denominator. So again, if I were to plug in a 1 here and here, that's what's going to give us a non-zero number over 0. So let's go ahead and put our vertical asymptote there at x equals 1. And notice that if I plug in any number that's less than 1, so if I plug in 0 for x, I'm going to get an imaginary number down here, and we're not dealing with imaginary numbers at this level of calculus, so we'll just say there's no output. If I were to plug in any other number that's less than 1, whether it be -7, or whether it be just something that's close to 1, but not quite, like 0.9, any number that's less than 1 will not give us an output. Less than or equal to 1, technically. So what that tells us is that graphically, there is not going to be any part of the function over here. All these x values are not in the function's domain, we would say. So think back to domain and range finding activities that we did in pre-calc, where we would say that the domain here looks like it's going to be 1 to infinity. That should not be totally foreign to you. All right, so what happens when I do plug in a number that's bigger than 1? Well, let's just put in a 2, for example. F of 2, I could see that my output is going to be equal to 1 over 1 there, which is just 1. That's a pretty easy one to compute. So if I go 2 over, that would give me 1 up. So let's just put a point there. What happens when I get closer to that vertical asymptote? What if I were to just plug in a number that was like 1.1 or 1.01? What about 1.0001? And if you'll recall in the recent video on infinite limits, that's where I'd say we do something like 1 over square root of a tiny number. And again, that wasn't really a tiny positive number. That wasn't really the way that I've seen any book express it, but that's just how it makes sense to me, and I hope you've got a sensibility about that as well. That when you have 1 over square root of a tiny positive number, you're going to get a big number, a big positive number. Or you're going to get something that's approaching infinity. And the purpose of all that is for us to just recognize that we're getting an asymptote that doesn't go down to negative infinity, but instead goes up to positive infinity. And what happens is x gets bigger and bigger and bigger. What if I were to plug in, I'm going to choose something very convenient here. What if I were to plug in 10? That's very convenient because that means that 10 minus 1 is a perfect square. And so I could tell that I get an output of 1/3. What if I were to plug in 101? That's another convenient one because then I would get 1/10 as my output. 1 over square root of 100, right? So I can tell that as x gets bigger and bigger and bigger, my output just becomes smaller and smaller numbers that are still positive. So my point is, while that may have seemed like a lot of work, students always complain that it feels like a lot of work at first. When you're well practiced at it, you can pretty quickly come up with a mental image of what this function is going to look like. So we have a sense of what f of x looks like now, right? And the line, while I've been making a big deal recently that point slope form is our preferred form in calculus, I will admit that in this case, let's go ahead and just, we'll find ourselves probably better off to just put this in slope intercept form. That's the mx plus b. We call it slope intercept form because when we rearrange it in that way, I've got the slope there and negative 1/2. And the y-intercept turns out to be negative 7/2 or negative 3.5. And that allows us to very quickly say, okay, if this is negative 1, negative 2, negative 3, negative 4, I'm running a little low on space here. But if I just shrink this a little bit, I can finish my depiction here. That tells us that we have a y-intercept of negative 3.5, negative 7/2, and we've got a slope of negative 1/2. So this thing's going to be going downhill like this in a rather shallow manner. So what does all this do for us? Why do I need a mental image? Again, we want to have a sense of what we're looking for. And what all this tells me is that we should expect one solution, which the wording of the problem suggested, but it's good to have that confirmed. So if this blue line represents the line that we're looking for, that is parallel to the green line and tangent to the red curve, that's the line we're looking for. And I also have an anticipation as far as what x and y values I'm going to deal with. I'm going to expect to find a point of tangency here and have some sense of how big that x and y value are going to be. All right, so let's put that off to the side. I should be bringing that back later. But let's start in on the algebra. And again, our first task is to find the derivative of f, which again is what we use to find the slope of the tangent line, which is ultimately going to be the slope of this line here. So move this off to the side. And hold your breath. This is going to be a bit messy. This is about as messy a derivative as you're ever going to calculate using the limit notation. I am hinting at the fact that we will eventually discover some little more efficient tricks for finding derivatives. But for right now, we got to go old school and earn our right to use those efficient tricks. So I trust that by now you are familiar enough with the derivative. And if you're not, I ask that you go back and watch the preceding video. Make sure you absolutely understand that you're not just memorizing this formula. You absolutely understand what we're doing here and what each piece of this formula means, that we're taking a slope. We're just doing rise over run. So here is our y2 minus y1 over x2 minus x1. But again, I'm just writing it out in this more grown-up form. And typically you'll see that x and the minus x on the bottom are typically not included. So this is the formula that you most often see. But I need you to constantly remind you, this is nothing more than rise over run. And this simply says that I want the 2 points on the curve to be as close together as possible, infinitesimally close. And that's what's going to give us our tangent line. So let's jump into the algebra here. If I've got f of x up there, and I want to ask myself, what am I going to put for that? Well, f of x plus delta x, I always conceptualize this as erasing the x and replacing it with x plus delta x. And that's all supposed to be inside the parentheses. X plus delta x, right? Erase the x, replace with x plus delta x. So what I've got here is 1 over square root x plus delta x minus 1. Now, as far as the minus f of x here, let's just erase my little embellishments here and get rid of these and go back to my original f of x. And so here's minus the original square root x minus 1. And that is all over the delta x. One thing that students do that kind of drives me nuts is that they'll just focus on this part of the equation and they won't write the lim or they won't write the denominator, and trust me, it gets them all screwed up and it just makes it hard to follow their work. So don't be lazy. It doesn't take long just to write these little extra pieces. All right, so what do we do at this point? Well, up top in the numerator of this larger fraction, we see two smaller fractions. We see a fraction minus another fraction, and we know that that means we're going to be doing some common denominator action here, right? So let's move this over. Just in the name of efficiency, I'm going to go ahead and continue it on this line here rather than do a new line. And let's think of what we need to put here and here in order to get our common denominator. Whatever quantities I write in those sets of parentheses need to equal 1. I'm not allowed to change the value of this expression. So if I put root x minus 1 down here to make my common denominator, I better put it up here as well. And over here, I'm going to put root x plus delta x minus 1. And then I'll do the same thing, of course, up top. So now up top, I've got a common denominator. This denominator is equal to this one. And with experience, you start to realize that no, we don't want to FOIL out that denominator. We're just going to let it hang there and focus on the numerator. And we have a little faith that things are going to work out in the end. Sometimes it takes a lot of faith here. But again, let's focus on that common denominator. That's what I'm going to write first here. And again, just write it out. X plus delta x minus 1 and cross your fingers. And up top, I'm now going to write this numerator minus this numerator, all over that same common denominator. So root x minus 1 minus square root x plus delta x minus 1. And I'll acknowledge that for a student who's new to this is a little bit scary territory. It feels very messy and you're worried that you're wasting your time and that you're doing something wrong, but trust me, this is going to work out. And if it isn't, I'll stop the video and redo it so that you'll never see my mistakes. Ha ha ha. All right, so what do we do with this? I hope you're comfortable enough now. You're at the point in dealing with fractions that you recognize you can just take this denominator and put it right here. If you're not 100% comfortable with that, I don't want you just taking my word for it. Think about how you normally divide fractions. Think about how you would take this big numerator and divide it by this. You would multiply by the reciprocal of this, right? So think about how what you're really doing is you're multiplying by 1 over delta x. That's really what we're doing. And then you see a little more clearly how that delta x appears over here. Okay? So just so I'm not being messy here, let me go ahead and write it on the next line. All right. And I'm also anticipating my next move as well. So I'm going to leave myself a little bit of room, make sure I have enough room to do what I'm going to do next. Up top, I've got root x minus 1 minus root x plus delta x minus 1. And that's all over this denominator. I tend to like to put this out in front. That's just a bit of a personal preference. So I'm going to put that first, delta x, and then times this. And avoid any temptation, again, to try simplifying that denominator there. Let's just let it hang and hope that some of it will go away in a moment. And with experience, you start to get a sense as to when it will go away and when you've just hit a roadblock. So, do you recall what we're going to put here? How are we going to clean this up? We've still got something that is indeterminate form. I should take a moment to point that out. Notice that if you tried direct substitution at this point, you would get a 0 down here in the denominator, and that would render the whole denominator equal to 0. And when you put a 0 up here, that means that this term and this term are equal to each other, so you get a 0 up top. So recognize that this is indeterminate form. And do you remember how we handle that? Do you remember the difference of squares form, where we think of this as a minus b? So we're going to do the a plus b, and recall how that helps us out. So you've got a pretty extensive bag of tricks here, and we just got to juggle all these skills, all the tricks in our bag, and confidently know what trick to use when. So again, this is another case where whatever I put in the top of the fraction, I need to repeat it down below. And I have to admit, that denominator is looking really nasty right now, but let's keep going. I think the clouds are about to part. The sun's about to shine through here. So, do you remember which one we should FOIL out? Should we FOIL out the top or should we FOIL out the bottom? We will FOIL out the top and just see what happens. So, since this fits our difference of squares form, a minus b times a plus b, I know that that's going to clean up a little bit. I know that I can just do this times this will give me x minus 1. And I know that my outer and inner terms are going to cancel each other out in that difference of squares format. And then I just need to subtract this times this, which will just cancel out the square root sign. So we're starting to see the clouds parting here. We're seeing that all the radicals have left us up top, and that's a good thing. Let's remember to put the parentheses here, and that we're going to distribute that negative sign. Now I'm going to admit here, for all the preaching I do about not being lazy, I'm going to make one little exception here. And as far as when I make exceptions and when I don't, that's something that we'll continue to discuss in class. I do feel like I have justifiable reasons for when I allow students to be lazy and when I don't. But here's what I'm going to do. I'm going to say all that ugliness down below, I'll admit that's a bit much. Let's just do that. I want to at least put something that reminds me that there's something there. What I protest against is students just leaving it blank. That's what causes problems, in my opinion. So let's at least put a scribble there and say, okay, I know there's something down there. And the reason I felt the need to do that is because I'm really just focusing on the numerator here, and I see that the numerator is going to clean up quite nicely, isn't it? If I'm just going to mentally distribute this. So if I'm going to have an x minus this x, I can tell those are going to cancel out. And I have a minus 1 here, and I have a minus negative 1. I can tell that's also going to cancel out. Now, if you'd rather not do this mentally, of course, I have no objection if you want to write this out. It might actually, until you become experienced with this, that might be the best thing to do. But you see what I'm going to have up top, and you see why it would be a mistake to simply put delta x up top? It's because I still have to distribute that negative sign. So again, be careful, but I'm going to go ahead and do that. I feel like I've got enough experience to do that. And I notice that that's going to cancel out with the delta x down below here. So once again, I'm going to allow myself a little bit of laziness. I'm going to put a delta x here, and then I'm going to put, some parentheses in the scribble, and that scribble represents all this stuff. But at least I'm putting something to represent all that junk that I'm not writing. And that's what I'm suggesting to you as a student that I'll be okay with. All right, so where do we do from here? This is where we had indeterminate form, but how do we plug the hole? That's where this delta x and this delta x will plug the hole when I cross them out. And now I'm going to stop being lazy and just write out the whole thing, because I can sense I'm getting close to the finish line here, at least as far as getting the derivative, which really is the bulk of this problem. So I've got a negative 1 up top, and down below I've got a square root. I'm looking right here right now. X plus delta x minus 1 times root x minus 1 times parentheses, and this is, boy, you just got to be real careful that you get all the parentheses right and any negative signs that need to be distributed. This is so easy to make goofy algebra errors here. But this is where we're at. And this is where you start getting excited because you feel you're getting close to something good here. Now that the hole is plugged, I can do my direct substitution. So equals, and I'll go ahead and plug in the delta x going to 0. Make sure you plug in 0 just for delta x and not x. And what that's going to give us, the lim goes away at this point, and what that gives us is, again, I'm plugging in a 0 here and here, and so I've got root x minus 1 times another root x minus 1, that's these two right here, times parentheses root x minus 1 plus root x minus 1. And again, I repeat, this is about as ugly a limit definition of derivative problem as you're ever going to do. So let's simplify that. Root x minus 1 times root x minus 1 is going to give us just an x minus 1 on the bottom. Root x minus 1 plus root x minus 1 is going to give us 2 root x minus 1. Now, instead of writing 2 root x minus 1 for that, I'm going to anticipate my next move and write 2 x minus 1 to the 1/2. That's the same thing as root x minus 1, right? And that means that my final derivative, oops, I just noticed, I forgot a negative sign up there, that's a big deal, equals negative 1 over, think of how I multiply x minus 1 to the 1 power times x minus 1 to the 1/2 power. I add the exponents, and that's going to give me 2 x minus 1 to the 3/2. And guess what? We have our derivative of f. And I'm going to go ahead and just, since I'm done with the derivative at least, put equals f prime of x. I'm going to put a box around it, but guess what? You remember, we're not really even done with this problem. Aren't you glad you signed up for AP Calc? This is the good stuff. But the good news is, seriously, we finished the hard part. We finished the hard work. And remember, this is the expression, or this is the function that will tell us the slope at any point along the f of x curve. So let's go back and remind ourselves what we have to do at this point. This is where, remember how we were going to set the, I know this is getting a little messy up here. Let me scoot down. So this expression here gives us, will tell us the slope at anywhere along this f of x curve. And we were going to set that derivative equal to the slope of this line. And do you remember what the slope of that line is? Do you remember how the equation of that line in slope-intercept form was y equals negative 1/2 x minus 7/2? So we're going to set the derivative equal to that slope of negative 1/2. So let's do that. Let's set negative 1 over 2 times x minus 1 to the 3/2 equal to negative 1/2. And let's proceed to solve algebraically. And when we solve this, and we're going to get an x value as our solution, what that's going to tell us is it's going to tell us this x value right here, the x value of that point. It's going to tell us what this x value is, and that'll help us proceed to go on and find the equation for the line itself. All right, so let's cross multiply there, and if I do 2x minus 1 to the 3/2 times negative 1, I'll get negative 2 x minus 1 to the 3/2. I'm going to set that equal to negative 1 times 2. That's going to give us negative 2. I'll divide both sides by negative 2. I'm going a little bit quickly here. This is pretty basic algebra that hopefully you feel comfortable with. Equals 1. I will then raise both sides to the 2/3 power to get rid of that exponent. And I know it doesn't really make a difference here on the right side, but I'll clearly show my work anyway. And that's going to tell me that x minus 1 equals just 1, right? And that tells me that x equals 2. And again, what does that tell us? That is the x value over here on the graph. So let's go ahead and label that on the picture. It's not a perfect, really well-scaled picture, but that's telling us that that value is 2. And if we want to find the equation for this blue line here, we're getting really close. We've got this x value. What we're going to do is we're going to find this y value right here of that point, and then we've got the slope already. It's -1/2, and we are almost done. So I appreciate you hanging with me so far. Let's go ahead and take this one home. So we've got x equals 2. How are we going to find the y value? Well, plug it into this function right here. So f of 2 is going to give me 1 over root 2 minus 1, which is just going to equal 1. So that tells me that 2, 1 are the coordinates of the point of tangency. And now, it's just when it's getting a little bit too messy here, again, hang with me here, let's go ahead and go to our point-slope form. This is the one that I keep saying is going to be our best friend in AP Calc. So that's our point-slope form. And one thing I should point out, I'm going to admit it's a little bit confusing. We just calculated an x and a y value. Those are really our x1 and y1 values. So let's plug those in for x1 and y1. Again, x1 is that 2 that I just calculated, and y1 is the 1 that I just calculated. And we said the slope is going to be -1/2 at that point. Let's fill in the rest of this. Whoops. Don't need an equal sign there. I meant a minus sign there. So that is a totally valid final answer. On my test and on an AP exam, I would invite you to leave it right there. The only reason to go any further is if you want to check it with a calculator, or if I were to tell you you had to go further, although I can't ever remember doing that. So we'll check with the calculator in just a moment. So let's go ahead and put that in slope-intercept form, just for the purposes of checking. And that would give me y equals, let's see, -1/2 x. When I distribute the -1/2 times -2, that's going to be +1. And then I'm going to add this one over, and that's going to be +2. So here is the slope-intercept form. And let's bring up the calculator, and this is the moment of truth. Let's bring up the calculator, and here what I have shown are the function itself, the original function itself, 1 over root x minus 1. And I also typed in the slope-intercept form of the line that we're supposed to be parallel to. So there's the function, which is pretty much what we predicted it would look like. And you see the line that we're supposed to be parallel to. And let's go to our y equals and plug in for y3, -1/2 x. I'm just going to do -0.5 x plus 2. And graph it and hold our breath. And there it is. What we see here is a line that is parallel to the given line, and it appears to be tangent to the curve. And we could do some other things on the calculator to validate that it's truly tangent there, but this is pretty compelling evidence that we did everything correctly. Of course, if you had any questions along the way, please get in contact with me, and if there's a particular part of the video that you found confusing, it would be helpful too, since this is a rather long video. Tell me at what time in the video you had an issue with.